to Professor Motohoco Mulase of lattice points on the moduli space of curves.
Thank you very much for the introduction. And also, I'd like to thank organizers to allow me to come here as a student. I've been learning a lot in 3 weeks, filling my notes. So I'm very happy to be able to expose to this stimulating environment.
You have a laser power. You're going to keep that for 100 years?
100 years. Yeah, your theory will last for another 80 years. Right? It's already lasted 20 years. Okay, so the title is about lattice point counting of the moduli space, which probably appear at the very end of the talk. The motivation of this talk is to understand the Énard-Orantin theory. It is already several years old. Then, well, of course, physicists have their own understanding, and then some mathematicians probably have their own understanding. We would like to really have a good grasp about it. So that's the motivation. And then, therefore, maybe it's better to start with what it is. And then in the first week of summer school, I've been talking about too many, I spoke too many times about Énard-Orantin. Finally, Pandari Pandey joked that, you know what? Grenoble is kind of looked down by Énard. One of the mountains surrounding Grenoble is named after him. Oh, gee, it doesn't matter. So what is Énard-Orantin theory? Well, maybe I should start from here. There are inputs. So input, you take an open Riemann surface. As appeared in the talk of Denis. And then that is actually included or embedded in C2. So it is not really an intrinsic object. We need extrinsic information also. And then, of course, C2 is a coordinate plane. So you have x coordinate and the y coordinate. Then we assume both x and y are simply ramified. So these are the assumptions. Then one more input is the differentiation kernel function. So W02, the indices will be explained in a moment. This will be a meromorphic section of C cross C over the KC, so one form over C, a symmetric tensor product, and then a tensor with twice of the diagonal. So this is a diagonal. So you do have a quadratic pole. Now, of course, in a local coordinate, probably, since curve is embedded plane curve, usually it is OK to use local coordinate. So in terms of local coordinate, it looks like dz1, dz2. So it's a symmetric differential form, not an exterior product. And then z1 minus z2 squared, and then plus holomorphic terms. There is no residue terms in the second part, namely no simple pole over there. And then what it does is C cross C going down C to the first factor, second factor, W02 lives on here. And then whenever you have a meromorphic function f on one side, you pull back, multiply, and then push forward. Push forward is indeed a residue map along the diagonal. What you get is df. So that is what the W02 is for the general curve. P1k is the first term is good enough. So these are the input. And then output is the following. So for that, we have an output. So output would be labeled by G and N, and then which is an object of symmetric tensor of differential forms. So it is a KC, KC, I should probably introduce the divisor D. So let's let the divisor D is a zero divisor of the derivative of x, which means since it is a simply ramified mapping, I'm talking about the sum of all simple ramification points. M. So P1 up to Pn are simple ramification points of this projection map. Oh, I'm sorry. Yeah, from here, C go all the way go down to. So curve C goes down to C. So it's a X is a map from C down to the complex line. Then the simple ramification points I'm choosing here. So this tensored n times. So it is a meromorphic section of symmetric differential one forms, and then having some order of poles at these ramification points. So it is no longer singular on the diagonal. So therefore, I have to say that this is true when 2g minus 2 plus n is strictly positive. And then, so that's an output. And then how you define it is the recursion formula. So that let me just write. So please go to see Jardin. Should I leave it here? Probably they are all in the mountains. Huh? I can use the other board. That's a good suggestion, but I'd like to leave the recursion. Most unlikely. So let me just use whatever available here, because I need only a small space. So WGN, yeah, again, let me use local coordinate. So this is the probably only one long formula I write today. I decided not to do it anymore. So this is equal to 1 over 2 pi I, and then the summation alpha runs from 1 to m, referring to the ramification points. And then integral, where I'd like to integrate over the z variable minus p alpha is equal to epsilon. So you take a small circle around it. And then I have to define this kernel function. So z1 and then z. And then multiplication of a big thing here. So first one, we want to get the g and the n object. First one is g minus 1, n plus 1. And then therefore, you have a little larger number of slots. So I insert z and then s sub alpha of z, which I define in a minute. So first one is this. And then next one is a summation prime g1 plus g2 is equal to g. And then index set I and j is a disjoint union of indices after 1 of wg1, and then index set I cardinality plus 1, and then a z sub I, probably is easy to understand, just all indices inside the capital I are appearing here, and then a wg2, j plus 1, s alpha of z, and then z sub j, and then bracket close. And then the easiest thing to explain is that what the sigma prime means is it omits the terms with involving W01. So W01 isn't really defined. So whenever you encounter that kind of thing, you don't include that term. it is not equal to saying that the W01 is equal to 0. No, it is not. So that's yes, yes. I'm going to write. So I'm erasing here, but we are assuming that a projection X is has only simple ramification. So locally, your curve looks like this, and then the point P alpha is here, and then the X projection is here. So what we want to do is that for any point Z near P alpha, we'd like to take the Galois conjugate of Z of this covering simply this is a deck transformation. So deck transformation isn't globally defined, only locally, but the formula doesn't require global definition. It's a residue calculation, so if you define this locally, that's fine. So that's the first thing. And then kernel, which actually, did I write Z1Z? Is a kernel defined as a ratio. This is an algebraic operator. First, you multiply. So usually I sometimes switch which I don't remember. So Z to S alpha Z. Z to S sub alpha Z, and then W02, and then Z1 is in here. And then, so W02 was defined to be the symmetric differential form. So I'm integrating with respect to the second slot from Z to S alpha Z. And then therefore still there is one differential form. Z1 is remaining here. And then here, this is YZ minus YS alpha. So most likely it should be of Z and dx as a function of Z. So, so this is a definition. So what it does is actually multiplication of dz1 and then contraction of dz. So in the bottom you have a differential operator, which I mean differential form, which means that you are contracting by the corresponding vector field. So that's a kernel operation. And then I'd like to emphasize that this is not like a two-term kernel operation. So Z appears here, here, and again here. So three terms. Or Z appears here, here, and then there. So the first remark I have to make is that this formula, what you are seeing, is not really a degeneration. It's not really the degeneration formula you usually normally expect on MGN. Actually, it is not a codimension 1 degeneration type of thing. What is happening here, if you look at the complexity, so 2g minus 2 plus n, if you consider this as a complexity of the quantity, then left-hand side and the right-hand side compared, this goes exactly down by 1. So all possibilities of making this quantity minus 1 is appearing on the right-hand side. Yes?
So this looks very dissymmetric in Z1 and the other value.
Right. They are, actually, this would be a symmetric differential form. So I didn't say that, but this is a symmetric automatically by this definition, symmetric differential form. Of degree n. Yeah, thank you. So it is a symmetric differential form.
But even with respect to Newton, the coordinates and CPN,
No, the formula doesn't tell you immediately why this is symmetric. So later, what they are when I talk about, you would understand why they would be symmetric. But from this point, the proving this being symmetric, you really have to do it several times to try to see once you switch what happens. So because this recursion starts from the very beginning, which is symmetric. W02 is the only thing you need, which is symmetric, and then everything you build. So no matter how you interchange variables, you get the same thing. Well, you have to prove. But later, when the geometry comes, you'll see immediately why they should be.
I'm sorry, so the WGN is global section of?
Yes, global section, but having a pose at D.
Yeah, so but it's really, so when you take this, is that the same as global section of C, KC, then with pole and D, and take this to the, take the n direct sum of this?
Not direct sum, tensor product I'm talking about.
Yeah.
So the product, yes. So they always, it looks like a dz1 dot 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 dzn. So this is the form, and then the function you do have would have a pose at each variable when each variable reaches to the coordinate of simple ramification point, you have a pole. So that's a kind of structure. Okay, let's see. So conjectures. Well, that's a nice formalism, but if you don't have any context, why do you care? So, two conjectures. There are many conjectures I'd like to talk about. So first one, 2-1, is the remodeling conjecture due to Marino, then more refined and a complete version, Bouchard, Clem, Marino, and then the Paschetti, 2000, maybe 7 also. So there weren't any time after this recursion was proposed. So what they did was the following. So let's let x be the Calabi-Yau. So x is a Calabi-Yau threefold. And then assuming it's toric, so that it's not compact. And then let's take beta, as usual, to be homology cycle. And then define G beta to be equal to the degree of the virtual fundamental class of this moduli space of stable maps or morphisms from a curve to X with a class beta. And then we learned in the first 2 weeks that this has a virtual dimension 0. So you can simply define the degree. And then this is a number. It's a rational number. And then let's define Fg is equal to summation beta. So in the summation, you have an object in the Novikov ring. So Ng beta q to the power beta. So let's make this kind of formal expression. So it does depend on the multi-parameter q. So this is the generating function of the Gromov-Witten invariance for this case. And then let's let x check to be the mirror dual. Which is, in this case, actually a family. It is a family of conic fibrations on C star plus C star, discussed by Renzo yesterday probably, also degenerating along a curve C, which, of course, since it's a family, let me just introduce U as a family parameter, which is inside C star cross C star. So you do have, in this case, a family of curves, or a curve depending on some parameter sitting inside the plane. Now, in the first presentation, I didn't mention that the plane can be replaced to C star cross C star. It changes the theory, but you can do that. Then the conjecture those physicists discovered is the following. So apply the Enach or Hantan formalism to compute this WGN, of course, depending on maybe parameter U of Z. Yeah, because you have a curve, you have X and Y, and then W02 is an intrinsic object of the curve. It doesn't depend on extrinsic thing. So all the ingredients are given, so you can immediately compute this thing. And then define Fg to be equal to negative 1 to the power g divided by 2 minus 2g of 1 over 2 pi I of the residue z minus p. I'm sorry, I have to take a summation with respect to alpha. So 1 over 2 pi I summation alpha. And then phi of z times W01 of z. And then phi satisfies that d phi is equal to y dx. So phi is just an integral or primitive of this one form, y dx restricted on the curve. And then you use this residue calculation to compute this function g, compute this constant g. So Fg is actually constant, but implicitly depending on the parameter u. Now, conjecture. Fg given over this panel is equal to Fg given on the panel here. So they are the same thing. WG1. W01 is prohibited still. Yes, so therefore, let's assume that the G is greater than or equal to 2, because apparently G equal to 1 is trouble.
So, sorry, so you define that there is plane curve, and here you restrict it to C star to C star. So you just apply it.
Yeah, you apply the formalism to this mirror curve, which is a degeneration locus of the conic fibration.
So, and you still project that to, well, now you project it to C star.
Yeah, right. That's right. And then, of course, this equality, after, of course, using or plugging in the mirror map. So Q is equal to exponential minus T. T is a Kähler parameter, and then U is a holomorphic parameter. You have to match them. And then the matching is, in these cases, it is already done by mathematicians. And then this paper, BKMP paper, specifies exactly what you have to match. So after matching, Fg is equal to Fg. So that's a first conjecture. But then what is kind of amazing is that so Fg is, suppose Fg is what we want to compute because it's a generating function of the Gromov-Witten invariance. This procedure suggests that Fg cannot be directly calculated from like F0, F1, F2, and so on. You have to go through WGN. So what is happening here? So let me just draw a picture. So this is a g-axis, and then this is n-axis. So this is n equal to 0, and then g equal to g. That directly comes from G1, WG1. But then to compute WG1, you do need WG minus 1, n plus 1. So you need this information. So all the way up. Therefore, for any Gn, what Gn comes from g minus 1, n plus 1, and then also the same g, n minus 1. These are both reducing to g minus 2 plus n by 1. So these contribute here. Sorry. Therefore, in order to compute fg here, you need all these information. You don't need actually smaller fg's. But in this region, everything has to be computed. Then you get fg here. So that's a suggestion we see from here. And then, of course, the conjecture continues. Wgn itself is a generating function. Of open Gromov-Witten invariance of x. So here, explanation is necessary. What do we mean by open Gromov-Witten invariance? So you choose a Lagrangian inside x, and then they use this class of Lagrangians, which is topologically isomorphic to C cross a circle. And then this circle actually is a one real cycle on the fixed curve inside the toric action of x. So that's what you choose this circle. And then look at the situation. So you map this into x, and then you have this c direction and the little circle direction, and it should be a cycle on a fixed torus, a fixed curve. So what kind of boundary condition you want to give? So in this case, maybe this map is f. So f of the boundary, so let me call this surface with boundary. So now this is a Riemann surface with the boundaries. So boundary of surface is mapped to L, and then f star of this surface class is equal to beta, which is now the second homology, relative homology, x and then L. And then the boundary condition is that how many times each boundary wraps around this S1. So you put mu1, mu2 up to mu n. So mu is equal to mu1 dot 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 mu n is an integer vector that specifies a boundary condition. So that's a situation. And then what you really wish to do is to identify something like this. So n, g, n, and then mu, maybe n, g, n, beta, and then mu. Mu is an integer vector. So this should be defined mathematically. So that's a open Gromov-Witten invariance somehow should be defined. So for individual example of toric Calabi-Yau cases, these are defined. So what I'd like to do now is actually try to interpret a little bit. So 2.2, let me call this as a working hypothesis. So it's a Laplace transform conjecture. It is not really a nicely formulated conjecture. It's more like a working hypothesis. What I'd like to say is the following here. So let's suppose you did get this kind of quantity. And then let's define Fgn of mu to be the same way. Beta runs in the relative homology cycle. So as before, we introduce this quantity. Then number 1, let's compute this as a, or consider this as a function of integer vector mu, and then compute its Laplace transform. So define fgn of z in variables to be equal to summation with this all possible boundary conditions of this number fgn mu, and then exponential minus summation mu I zi. So let's define this way. And then also wgn of z to be simply dz1 dot 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 dzn. So these are exterior differentiation of this function you just defined above. So this is again a definition. So what I'd like to say is that, probably it is better to use some example to see what I want to say, is usually the quantity, the collection of all these numbers satisfy a combinatorial recursion, combinatorial relation based on what I have to say. This is afternoon, after lunch, so let me just say it. Relation based on the, so let me just write. I cannot really pronounce when you are taped. Removal of a pair of pants. So, what? Since you are now talking about open, I'm sorry, not open, bordered Riemann surface, you can cut along things. And then there are several ways you can do that. And then that would change the combination of g, n, and even beta, and of course mu. So what you can do is, suppose you have surface like this, you can cut it off. And in this case, you are keeping the genus intact and then reduce the number of boundary cycles by 1. Or you can just do, say, this kind of thing. Suppose you have originally genus G situation. And then by cutting off or removing the pair of pants, you are reducing the number of genus by 1 and then increasing the number of boundary cycles by 1 here. Or totally disjointly cut out the bordered Riemann surface into 2 pieces. So these 3 cases appear. Now, in the original, so this is actually remodeling B model, therefore this is on the B model side. You don't have any kind of such geometric object. G and N don't represent anything geometrically. But when you go to the A side, you do see those geometric objects. And then therefore, by looking at how you deal with the domain, so by changing the domain, you would expect to see some kind of combinatorial relation among these quantities. Well, still, this is a kind of a hope. It's not really a conjecture. It's a hope. So suppose you have done that, then 3. So this Laplace transform hypothesis is that the Laplace transform of this combinatorial relation should be equal to the NR1, provided that this W is indeed what the BK and P are talking about as a W. So this W should be coming from the Laplace transform of this open. Yes?
So when you have this variable C1 over Cn, does that mean that you have the various boundary components live on different Lagrangians?
Lagrangian is said to be only one at this moment. So I'm just mapping all boundary to the single Lagrangian.
But the Z-lines are coordinated on the curve C. The curve C are different.
So actually, they are actually marking these boundary conditions. So I'm taking the Laplace transform with respect to the wrapping. So what do you mean by Laplace transform? This is simply a generating function of this quantity with respect to the wrapping. But then instead of saying this is a generating function, I want to make this as a transform so that whenever you have a combinatorial relation among them, that would translate into a relation among this. And after differentiation, I'm saying that that should be that NR1 equation. So that is a...
So in some sense, now you're working in a local coordinate chart because the Z1, Zn are complex variables, not coordinate vectors. Just in the chart.
Well, to answer your question, probably I should say the fourth part. C, the curve C, which appeared, I didn't give the name, N-hand Hontan calls it the spectral curve. Spectral curve is indeed the Riemann surface of, say, the F, maybe F is better, FG1Z. What do I mean by that? It's a domain of holomorphy. So FG1Z is a one variable function. Look at the region, the largest region where this function is holomorphic. And then this should be the curve in the other side appearing. So it's a domain of holomorphy of FG1Z. And then, of course, you take a symmetric product of all these. So that's a kind of...
What do you mean by domain holomorphy? Or is that you take?
Oh, so the Z, so as Denis said, this is just a parameter, right? Yeah. It's a conjugate parameter of the Laplace transform. Then you define a holomorphic function, and then you consider the domain at which the function is holomorphic, the largest domain. And that turns out to be, or should be, the curve C originally conceived in the conjecture.
This is C2 or
Yeah.
C star or C star?
Yeah, right. That C, the complex structure of that C is the same as this. So I'm not defining X or Y here. This is simply the, as an intrinsic curve, this is equal to that curve. That's all I'm saying.
How did you recover X and Y from that?
Yes. That is actually kind of analysis one has to compare of what you get. So I don't have any good answer at this moment. For the examples, you really have to compare and then find the function. But
I mean, one way to think about this is that C is exactly a local coordinate in the modular space of deformations with Lagrangian.
oh yes, yes.
And this is like a global version. The global modular space of Lagrangian is the curve C. The coordinates X and Y only come from the length of the vector.
Sorry, global what? Curve
C is the global modular space.
Right.
Of Lagrangian
That's right.
as object of the space.
That's right.
But can you see the curve?
Yes.
In this case, yes.
Oh, okay. So you mean the model space itself is the curve?
Yes.
Right.
Lagrangian is the curve.
That's right. Yeah, so that's how appearing in the toric
And
geometry
so
here.
third assertion means that this three process of removal of pair of pens correspond to that look like, I don't know, like splitting or.
Yes. So actually,
there are two operations, right? One
so
cutting the neck there.
this one is the first one, and then these two are actually corresponding to the second one, because here I am actually making W02 appearing here. So I excluded the W01, but as W02 are allowed. So you can cut this Riemann surface with the one piece unstable 02, and then the same genus and the other piece. So you take the pair pants out. So these two are the second line, put them together.
Yeah, but
Yeah, so first line corresponds to opening up this handle. And then these are the put together into the one thing. Okay, so then I just wanted to mention about third, more concrete conjecture. So 2.3, it's a conjecture by Bouchard and Marino. On single Hurwitz numbers. So single Hurwitz numbers, which actually I spoke about a lot in the last couple of weeks, so let me just be quick. Instead of considering this as a Gromov-Witten invariance of P1, we'd like to consider this as an open Gromov-Witten theory. So you have this bordered Riemann surface, and then you consider P1 as a symplectic manifold, and then you have a Lagrangian, which is actually a small circle around the point at infinity. And then you do the same thing. So this is a Lagrangian, therefore you have to constrain all these borders going to the circle, and then therefore they are parameterized by or specified by the wrapping number. And then you make a moduli space of this, but then you can just shrink that target curve to the point. Therefore, this would give you the Hurwitz scheme. And then the Hurwitz scheme, which actually covers projective space of dimension R. R is the number of simple ramification points of this, which is the generic such map. And of course, the projective space has only one natural top cohomology class. Therefore, in this case, if you do the open Gromov-Witten theory, the only natural invariant is this degree, which is a single Hurwitz number. So let me just write it as a Hg of a vector mu. Mu is an integer vector. So this is actually the degree of the branch morphism that Dmitry was talking about yesterday. And then I'm stressing that that is the only plausible open Gromov-Witten invariant in this context. There's nothing else because the space is so simple. So we consider this Hurwitz number as an open Gromov-Witten invariant. Then let's do everything here. But then, of course, in this case, we have to define the mirror dual of P1 in a reasonable way. But then here, let me use this kind of philosophy. So the mirror object should be a curve, which should be the domain of holomorphy of the Laplace transform. So that's what we did, actually. But before that, let me just say it, because we don't have the time to write it up. So the conjecture of Bouchard and Marino is that they come up with a function, actually. Yeah, let me just say FGN. They define this function, which is summation D1 plus dot 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 plus D sub n is equal to 3G, smaller 3G minus 3 plus n of this intersection number, tau d1, tau d sub n, wedge g check 1. So this is actually 1 minus lambda, the 1 plus lambda 2 minus and so on up to lambda g. So it's just an alternating sum of the Hodge classes of genus and then n marked. So on the modular space mgn bar, and then the product of some islands from 1 to n, xi sub d sub I of z sub I. So what Bouchard-Marino conjectured is they come up with a particular class of one variable meromorphic functions, and then they are recursively determined, and then say that form this expression, and then compute wgn is equal to dz1 to dzn fgn. Then this should satisfy the Hénard-Orantin recursion relation with respect to the following extrinsic data, namely x is equal to y exponential y minus 1 minus y, and then more or less y is equal to z itself.
Sorry, so what is, FGN is defined with the correlator without the product. What's the product? Is that related to FGN?
Yes, so what I said is that maybe I should write them down. They have given an explicit formula for these meromorphic functions in one variable, and then define this quantity. Okay, so they recursively define this function. Okay, and then I wrote this down. Of course, this comes from the ELSP formula. And then they differentiated this n times, defined the n form WGN. And then they said that let's consider the curve C defined by these two parameters. Okay. Then WGN as defined should satisfy the Hénard-Orantin recursion, by this way producing a lot of, quote, new relations among the linear Hodge integrals, which didn't seem to be known. Actually, it wasn't known at that time. So that was the content of their conjecture.
Okay, so the CD and DI is somehow defined elsewhere.
Defined, yes, elsewhere.
Correlator is just a coefficient of C.
Right. So this is again a generating function. But instead of calling this as, say, xdi, instead of doing that, they made a particular choice of functions. Yes, and then they realized that this derivative satisfies that equation.
There should be a relation with single Hurwitz number somewhere, right? Where is it at this point? So it's somewhere hidden in that.
Oh, yes. So single Hurwitz number is equal to the ELSP formula, and then this comes out. That is, of course, hidden in there. But then, so what I want to say is a mathematical result in the next panel, where maybe I just summarize only a few things. So what has been done? So first thing, the Bouchard-Marino conjecture is true. And then actually it is coming from the even more, namely the Laplace transform conjecture is true. So what you do is actually what the Bouchard and Marino defined. So let me just say this, maybe just a T. So you just do this. So this is a Laplace transform. Maybe I don't write even the formula. Laplace transform of Hg mu as a function of mu. So it's a function of integer variables, and then you compute its Laplace transform. And then after the Laplace transform, my Laplace transform coordinate was z. So what I want to do is to change the variable z into, well, maybe I don't want to do that here now. We have already done that kind of thing. So maybe I just don't do it. So you just compute the Laplace transform and then identify that this Laplace transform is indeed well defined on this curve. And then yes, that agrees with this expression. So to answering YP's question, this is actually coming as a Laplace transform of the factor mu to the power mu plus d divided by mu factorial e to the minus mu. So of course, without this, that is a factor appearing in the ELSP formula. And then you just compute its Laplace transform, you get those functions. And then one more thing is that Hg mu, all these quantities, satisfies or satisfy the cut and join equation defined by Dmitry yesterday. And then that cut and join equation is a combinatorial relation. As I say, you compute its Laplace transform. So Laplace transform of cut and join is indeed equal to NR in this case. So that is indeed true. So we are trying to say is that if you understand the Hurwitz, single Hurwitz number as an open Gromov-Witten theory instead of closed P1 Gromov-Witten theory, it's open, then you can do this a pair of pants removal. A pair of pants removal is actually changing 2g minus 2 plus n by 1, right? But then you remember that the number of simple ramification points is equal to this plus d. So if you don't want to change the degree d and then reducing r by 1, only thing you are doing is indeed removing a pair of pants. That's what you're doing. So cut and join equation is exactly this pair of pants reduction. And then you can take a Laplace transform, which explains what the kind of combinatorial situation appearing in the right-hand side or the B-model side of BKMP conjecture. So, and then I actually wanted to talk about this lattice point counting, which probably just go quickly. So instead of writing, let me simply say the this Laplace transform conjecture type of thing is actually used by Zhang-Zhou together with the combinatorial analysis Kefeng Liu, Melissa Liu, and Zhang-Zhou did for the solution of the Marino-Waffa formula, which they also called cut and join equation. They computed the Laplace transform of that cut and join equation, and then realized that that would solve the BKMP conjecture for the toric-Calabi-Yau threefold is actually C3. So for C3 case, it has been already done, and then the same analysis, same Laplace transform idea works over there. So I don't have time to go into there, but that's how it was done. Now let me just talk quickly about the very original Kontsevich work. So what he did was, of course, target space was considered to be point. But then if you carefully analyze what he did in his paper, he was not talking about a closed Gromov-Witten theory. He was talking about open Gromov-Witten theory. So what is the open Gromov-Witten invariant of a point? This is indeed the Euclidean volume of the moduli space. And then he does calculate the Laplace transform of that volume and then get the matrix integral expression. And then, of course, Euclidean volume of MGN, if you consider this as an open Gromov-Witten, they do satisfy the recursion relation among this. And then you compute the Laplace transform. Lo and behold, that is the Virasoro constraint condition. So that's a mechanism in the original Kontsevich work. You can read in that way also. Then last 3 minutes, what I'd like to say is that as a kind of natural generalization, when you have Euclidean volume, of course, what I'm talking about is that Kontsevich used this combinatorial model of MGN, which is totally non-algebra geometric. So it is probably hated by many algebraic geometers. This doesn't hold in any category other than topology. So topological, as a topological orbifold, there's an orbifold equality of these two. Here, right-hand side is a space of all ribbon graphs, as Kontsevich said. A ribbon graph means simply the one skeleton of a cell decomposition of an oriented, compact topological surface, right? And then you give the edge length, and then you make it into a complex that is equal to the moduli space times R plus N. And then this projection is a perimeter length map. So what I try to, what I want to say quickly now is that here you introduce the integral structure. So Z is naturally embedded in R, we believe, and then using that, include the integral structure. And then consider the inverse image. So what we have to really do is that for a ribbon graph gamma, you look at the inverse image, realize this as a polytope, because a graph gamma comes with the information of incidence matrix. So this corresponds to the incidence matrix. So you consider the number. So N actually stands for Norbury, because this is first considered by Paul Norbury of Australia. And then let me use mu. So this is a number of set of all integer vectors of length edge of a graph. And then incidence matrix applied to this edge is equal to the given perimeter length. So I choose the perimeter length to be something like a partition, and then divide by automorphism gamma. So nobody considered this number, which is naturally a rational number. And then he actually proposed that there should be a combinatorial recursion formula. And it was proved by my student, Kevin Chapman, and then Safnuk. So they do satisfy actually a topological, very simple combinatorial formula, so relation. So as you can expect, if you have a function in integer vector mu, I'd like to compute its Laplace transform. So I did. And then did the same thing, take a differential. Oh, they satisfied this NRO-Antan, namely this very simple relation here. So how does the relation come from? Here, actually, it has to be a gain pair pants removal. So what we do is to remove an edge. You have a ribbon graph. You remove all possible ways to remove the edge. Then you get a very, simple to prove recursion formula. Writing down is very long. It requires entire panel. So it's complicated, but a very elementary recursion or relation you can prove. You compute its Laplace transform. Then it again becomes this with the spectral curve or the B model side of the curve, which has actually two ramification points. So in this case, this is indeed the mirror of P1. So this curve appears, and then you have two ramification points, and then you have this all the structures, and then they satisfy that. So a little bit over time, but let me advertise a few things here. So we compute FGN of t, which is actually the Laplace transform of this Norbury's function. Several things we can say, so let me just say this. This is a Lohan polynomial. So again, it is a polynomial type of behavior. And then it is symmetric with respect to ti goes to 1 over ti. And then if you look at the top degree terms, you can explicitly calculate this expression, and then you get the two different expressions. And then these two you equate, you get Kontsevich's unique boxed formula in his original paper of 1991. That formula appears. So you have two different expressions, and then they are the same, which means actually this Enaho-Hantan recursion coming out of this result restricted the top degree term is again indeed the Virasoro constraint condition, and then therefore Virasoro constraint condition is exactly the edge removal operation. So it's just a Laplace transform of the edge removal is a Virasoro constraint condition. So that's one thing. And then the second thing is that this t goes to 1 over t has a fixed point, and then you evaluate this function at the fixed point. Then what you get is negative 1 to the power n Euler characteristic of MGN calculated by Hera and then Zagier long time ago. So that's a special value here. And then so this polynomial, or to be precise, one polynomial, gives you the psi class intersection numbers as well as Euler characteristic of MGN at the same time. And then a few more things I should say is that you can just do the same thing to compute FG without n. So what you get, this is actually Euler characteristic of MG. And then this FG can be done for the Hurwitz case. I didn't mention, but the Hurwitz case, FG is actually trivial. It's just 0, which is kind of strange. P1 case, there's no closed sector by some reason. Only open Gromov-Witten theory. So in this case, if you do the closed sector, this is just Euler characteristic of MG. And then the open sector, the special value is Euler characteristic of MGN. So how much can you go? Natural extension is, of course, changing the point to BG, and that's what we've been working with. Olivier Dumitrescu and then other people. And then probably the paper should be posted soon because everything seems to be going very well. Now, the real remodeling conjecture, at this moment, I'm not reaching very close yet. And thank you very much for your attention.
Since you say it's already known for 6-way, can you just do growing?
Yes. That's right. So that's. So we don't have a good control of this gluing at this moment. And then how can you come up with this combinatorial recursion? There is also a kind of cut and join for general situation, but then analysis seems to be a little bit daunting to compute its Laplace transform at this moment. So we tried these kind of things. We are hoping to see some better picture. If it is a gluing all what you need, then why don't we try to find the same structure in both sides and match? Because locally they are the same. The combinatorics will take care of other things. That may be a possibility. We don't know yet.
But actually, the B side, you're just some residue of the branch point, right?
Yes.
The branch point is likely decomposed.
Right.
Yeah.
Yes. So therefore, it may be simpler than what we are afraid of. Yeah.
How is this original Kontsevich area function matrix model encoded?
Yeah. So Kontsevich thing is actually x equal to y squared is coming as a limit from here of the infinity part and coming in here.